Dr. Ivy showed you what the motion of the ball that was released from the moving cart looked like in the Earth frame of reference and in the cart frame. The motion looked simpler from the cart. Now I want you to watch the motion of this white spot. You probably see the spot moving in a circle. But this is what its path is actually like in the Earth frame of reference. This is your normal frame of reference. You saw the spot moving in the circle because your eye moved along with the cart. You put yourself in the frame of reference of the moving cart. So you see, it isn't always true that we view motion from the Earth's frame of reference. When the motion is simpler from the moving frame, you automatically put yourself in that moving frame.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards? All right. If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction. And we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind. Here's the cart, which was moving along in this direction with a velocity u. We were sitting on the cart at a table. Here I am over on this side, and Dr. Hume was on this side, and we were pushing this puck back and forth on the table. When I pushed it, it went in this direction with a velocity v, and when Dr. Hume pushed it, it went in this direction with the same velocity v, but this is the velocity relative to the cart. What about the velocity relative to an observer on the ground in the fixed frame? Well, if it was pushed in this direction, its velocity is u plus v. If it's in this direction, its velocity is u minus v. This is all very reasonable. There's nothing very hard to understand here. The surprising thing about this expression is that it is not accurate in all circumstances. At very high speeds, and by high speeds I mean speeds close to the velocity of light, this expression breaks down. At these very high speeds, we have to use the ideas about relative motion developed by Albert Einstein in his special theory of relativity. However, for all the speeds that we are ever likely to run into, this expression, u plus or minus v, is completely adequate.
So far, we've been talking about frames of reference moving at a constant velocity relative to one another. Now I'm going to do the experiment with the dropping ball again, only this time the cart will be accelerated relative to the Earth frame. These weights will fall and give the cart a constant acceleration. I'll put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball was the same as it was before, only this time it landed in a different spot. This is because the car kept on accelerating in this direction as the ball was falling. Now I'm going to let you see it again with the slow motion camera fixed onto the cart. This time you saw the ball moving off to one side and not following down the vertical reference line as it did in the constant velocity case. Now suppose you were in this accelerated frame of reference. How could you explain this motion? Gravity is the only force acting on this ball, so it should fall straight down. But if the law of inertia is to hold, there must be a force pushing sideways on the ball in this direction to cause it to deviate from the vertical path. But what kind of a force is it? It isn't a gravitational or an electric or a nuclear force. In fact, it isn't a force at all, as we know one. So we're left to conclude that since there is no force that could be pushing in this direction on the ball, that the law of inertia just does not hold. This is a strange frame of reference. We call a frame of reference in which the law of inertia holds an inertial frame. The law of inertia holds in the Earth frame of reference, so it is an inertial frame. The cart moving at constant velocity relative to the Earth is an inertial frame, but the cart which is accelerated is not an inertial frame. Because the frame of reference that we're used to living in is one in which the law of inertia holds, when we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the frame see an acceleration of the ball in this direction, and you say that there is a force causing it.